this before we talk about what's in 11.3. Sorry, 11.4. I was thinking 11.3, so I wrote 11.3. Limits at infinity. All right, so what we've been talking about so far. We've been interested in the limit as x approaches some number. And that's when we did our dividing technique or our rationalizing technique. We get a 0 over 0, something like that. So we have more work to do. Today, we want the limit of our function as x approaches plus or minus infinity. So what we're saying here is what happens eventually. What happens as x gets really, really big? Or small? What happens as x gets really, 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 really small? Or as x gets really, 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 really big? What happens eventually? When did we talk about that before? What kind of asymptotes? Vertical would be x would be our function approaching infinity. That's when we divide by 0. Horizontal asymptotes. This is asking us about horizontal asymptotes. So our limits as x approaches in positive or negative infinity are the same thing as asking what is the horizontal asymptote of this function. That's what the limits at infinity are asking us about. We already know about horizontal asymptotes. We're using the same rules. So we don't have to learn anything, well, we don't have to learn much new. I'll put it that way. Do have to learn one little thing. So we're going to use the same rules. We need to know one thing. And we already know it. We're just going to write it down, make it formal. So what we're talking about, limits at infinity, we're talking about a horizontal asymptote rules. What happens eventually? So our main limit that we need to know for this is the limit as x approaches infinity of 1 over x to some power equals. If we divide 1 by something really, really big, what do we get? Something really, really small. So this limit, as x approaches infinity, as x keeps getting bigger and bigger and bigger, this limit is going to be 0. So that's our key limit for today. If the denominator gets really, really big, our limit gets close to 0. So what I'm going to do, we're just going to go through 3 examples because we only have 3 cases for horizontal asymptotes. Either the horizontal asymptote is y equals 0, the horizontal asymptote is y equals some number, so we did the ratio of the leading coefficients, or there's no horizontal asymptote. The limit doesn't exist. So I'm going to go through one example of each and talk about how we use this limit in those cases as well. All right, so questions before we go on. See, isn't this refreshing? We're learning a lesson that we already know. It's the best kind of lesson. So we can all say, oh, I remember that. Or I hope we can all say, I can remember that. I hope, especially as we're getting close to the final, that this refreshes your memory about these things. All right. We want to find the limit as x approaches infinity of 3x to the fourth minus 5 over x to the fourth. Actually, let me, yeah, this is fine. All right. For this function, we have the powers in the numerator. Highest power in the numerator and denominator are the same. So for our rules for horizontal asymptotes, what would we say the horizontal asymptote is? How do we find it? When our degree in the numerator and degree in the denominator are the same. The ratio of the leading coefficient. So y equals 3 over 1 is the horizontal asymptote. So we would say that limit, the limit equals 3. Because as x gets really big, our function approaches y equals 3. Now, you may have learned these terms in Algebra 2. I usually save them for limits. In this situation, when the degree in the numerator and the degree in the denominator are the same, we made this term up a couple of years ago because there wasn't a special name for this. I call it equal heaviness. Because the degree in the numerator and degree in the denominator are the same. The way I think of it, equal heaviness is I think of, like, for example, Pantera and Metallica. They're equally heavy. So if you, it might help you to think about some bands that are heavy bands. Metallica and Pantera are equally heavy. That's what we're talking about here. So they balance each other. So that we take the ratio of the leading coefficient. At first I said Metallica and Megadeth, but we all agreed that year that Metallica was heavier than Megadeth. I told my son maybe Five Finger Death Punch and Avenged Sevenfold, but he said no, he thinks Five Fingers is a little heavier. I'm not sure I agree with that. All right. Algebraically, so we call you if the problem doesn't ask you to show this algebraically, you can say the degree in the denominator and the degree in the numerator are the same. The horizontal asymptote is the ratio of the leading coefficient. If you said equal heaviness, the limit is 3, and the problem didn't ask you to show algebraically, you'd be fine. Algebraically, we only need one technique for limits at infinity algebraically. Divide everything by the highest power of x. So I'm going to say this is going to equal the limit as x approaches infinity. The highest power is x to the fourth, so I'm going to write it out explicitly here. 3x to the fourth over x to the fourth minus 5 over x to the fourth over x to the fourth over x to the fourth. Dividing everything by x to the fourth. So I'm multiplying the numerator and denominator by 1 over x to the fourth. Well, this is the limit as x approaches infinity. These cancel, and I get 3 minus 5 over x to the fourth over 1. As x approaches infinity, what does 5 over x to the fourth approach? 0. of 3 minus 0 over 1. So we're using this rule. This limit is 0, and my limit then is 3, the ratio of the leading coefficients. And this is actually why, when we talked about horizontal asymptotes, we said that we could use the limit of the ratio of the leading coefficients to find a horizontal asymptote, because the limit is 3. So horizontal asymptotes and limits are the same thing. Limits at infinity. Here, I'll write this so it shows up on the when I save this. Okay, just so we have a reference point. All right, let's look at another example. Everybody good there? Good with this algebraic technique. So if the problem says find the limit algebraically, this is what they're asking you to do. Divide everything by the highest power of x, and then use the limit, our main limit that we talked about. This limit here. All right, let's look at another example. The limit as x approaches infinity of x minus 1 over x squared. So the highest power in this one is in the denominator. So for our horizontal asymptote rules, when the highest power was in the denominator, what did we say was a horizontal asymptote? Y equals 0. I'm just going to write HA. So the limit is 0. As x gets really, really big, this function gets close to 0. We call this situation bottom heavy, because the denominator has the highest power. Yes?
If it were x approaches negative infinity, would it still be limit 0?
There you'd have to be careful, because a negative number squared is positive, but a negative minus a negative is, here, it would still be 0. But it would approach it from underneath, because it's always negative, so it would approach it from underneath. So we call this bottom heavy. I'm just going to put a thing, equal heaviness here, just so we have the term marked. So when we have a bottom heavy function, the limit is, as x approaches infinity, the limit is 0. So if the problem doesn't ask you to show algebraically, just says find the limit, you can say, oh, that's bottom heavy, the limit's 0. Algebraically, isn't algebraically a nice word? I like saying that word. Divide everything by the highest power of x. This is equal to the limit as x approaches infinity of the highest power of x is x squared. X over x squared minus 1 over x squared over x squared over x squared. X over x squared is 1 over x minus 1 over x squared over 1. As x approaches infinity, what does 1 over x approach? Using our main limit rule for this chapter. 0, not this chapter, this section. Minus, what does 1 over x approach? 1 over x squared. So that approaches 0 over 1. Well, this is just 0 over 1, which equals 0. So the limit is 0. And that's why we said that was our horizontal asymptote when the highest power was in the denominator, because we can show algebraically that the limit's 0. So that's a bottom heavy function. All right, questions there? Okay, let's look at one more example. The limit as x approaches infinity of x cubed minus 1 over x squared. So for our, we have the highest degree is in the numerator. When we had talked about a horizontal asymptote rules, what did we say when the highest power was in the numerator? What's that? No horizontal asymptote. So that meant that there's some other kind of asymptote, but it's not horizontal. So this tells us that the limit does not exist, because the function keeps getting bigger and bigger and bigger, or smaller and smaller and smaller. If we had a slant asymptote, the function eventually follows a line. So it gets bigger. We call this top heavy. So for a top heavy function, the limit does not exist, because there's no horizontal asymptote. Algebraically, divide everything by the highest power of x, highest power of our variable. So we get our highest power is x to the third. So x to the third over x to the third minus 1 over x to the third over x squared over x to the third. So that's the limit as x approaches infinity of 1 minus this limit. I'll write it out, x to the third over 1 over x. So this is the limit as x approaches infinity. We get 1. As x approaches infinity, 1 over x to the third approaches 0. 1 over x approaches 0. 1 over 0, which is undefined. So the limit does not exist. Our function approaches infinity, so our limit doesn't exist. So for limits at infinity, all we need to know is a top heavy, bottom heavy, or equal heaviness. And our algebraic technique, if we need to show that algebraically, divide everything by the highest power of x. Now, be careful. These concepts only apply for limits at infinity. So on the test, if we had something that says the limit as x approaches 1 of something, and you wrote, oh, it's top heavy, the limit doesn't exist, you would get 0 points, because those rules do not apply as x approaches a number. These rules that we talked about today only apply as x approaches positive or negative infinity. So don't try to apply these rules in other situations. These only apply when x approaches positive or negative infinity. So I'm thinking bottom heavy, that would be like a funk band, right? Where the bass is the lead. That's a bottom heavy band. Yeah, I think so. Or one of my favorite bands is Animals as leaders, and both guitar players play 8 and 9 string guitars. So that's kind of bottom heavy. Yeah. So it leads to an interesting philosophical conversation. It's interesting how math and metal are related. I've been telling you that all semester, but it's nice when we get a more concrete example. All right, questions? Yes? From here? The limit as x approaches infinity of 1 over x to the third. So I'm going back to this. 1 over, as x approaches infinity, the limit of 1 over x to something is always 0. Because we're dividing by something really, really big. So I was applying that here. And we could think of this individual function, that little piece is bottom heavy, so the limit is 0. This little piece is bottom heavy, so the limit is 0. So we get 1 over 0. Okay. Top heavy would that would be like an opera soprano maybe. That would be a top heavy function. The limit of how high the note the soprano can sing doesn't exist. You can sing higher and higher. Now, just so you know, if you apply this equal heaviness thing in your calculus class, your calculus teacher may not be familiar with that terminology. I've been working on popularizing it, but I've had limited success. Or what might happen is, oh, that's that thing that Mr. Beamer made up. But that's how ideas get popularized. Somebody makes it up, and then eventually